Hi, everyone. Thank you for having me. Thank you for coming to the talk. So in this talk, we will explore the potential of memory forensics being used against ransomware. Basically, the key concept is that ransomware depend on a set of keys or a single key in order to extract the ransom. And if we can take that leverage away from them by producing a duplicate copy of the key, then we can debilitate their attack. So a little bit about us. As mentioned, my name is Pranshu Bajpai. I recently graduated with a PhD from Michigan State University. I'm currently employed as a security architect at Motorola Solutions. And I co-wrote this paper with my advisor, Dr. Richard Enbody, who is a professor in the Department of Computer Science and Engineering at Michigan State. So we all know the problem of ransomware. Unfortunately, it's been a constant problem for more than a decade, and they have only increased in sophistication. What we're observing now is that they're learning from their past mistakes. They're coming up with better attack models, and the threat is constantly evolving. In the current scenario, for example, we've seen opportunistic attackers take advantage of the COVID-19 situation in order to cause more damage to data. So the problem of ransomware is clear. It's an unauthorized malicious software that performs encryption on your device. It's usually data encryption, and in order to obtain your data back, you have to pay the ransom. Most of these successful ransomware will use a hybrid encryption model, and we'll discuss the details of this in a moment. What a hybrid encryption model basically is a combination of symmetric and asymmetric encryption algorithms. And as you can imagine, because they depend on their crypto system to extract the ransom, key management becomes the central heart of this malicious software. So we'll be focusing a little bit on key management. Standard encryption algorithms are observed in ransomware simply because it's better to use. One of the fundamental rules of cryptography is don't roll your own crypto. So attackers understand that. In fact, some ransomware in the early days tried to come up with custom encryption algorithms that they were quickly decrypted. So they use standard encryption algorithms that are time tested, for example, AES, RSA. And another reason for using standard encryption algorithms is that all APIs support it. So on the victim's machine, there's a great likelihood that there's going to be an API already present that's going to support encryption with those standard algorithms. Briefly, I want to mention the NIST cybersecurity framework. NIST has proposed a cybersecurity framework which has 5 key actions in favor of cybersecurity: identify, detect, protect, respond, and recover. Most of the solutions proposed against ransomware today are observed to focus on detection, prevention, the early stages of this framework. However, few solutions exist that really address the later stages, which are response and recovery. So we want to focus more attention towards the response and recovery part. So assuming that the attacker is already in, what can we do from here? Backups are the only practical solution that exists right now in that space, and we want to augment that. There are 6 categories of ransomware virulence. In one of our earlier works, we discussed categories of ransomware because not all ransomware are the same. Some are more virulent than the others. And to that end, category 1 would be the simplest forms of ransomware, whereas category 6 will have a bulletproof crypto system such that if you're encrypted by one of these, then it is practically infeasible to recover the key without paying the ransom. So we'll be addressing category 6 ransomware in today's talk, the most effective variants. So this is the kill chain in modern ransomware that we've identified. These are key constraints on all that bind the activities of ransomware developers. As you can see, it begins with infiltration. Cryptographic ransomware that are encrypting data on the host must first infiltrate the host in order to encrypt the data. From there, they need to execute, otherwise they lie dormant as just a file on the machine. Preparation includes generating keys. Keys need to be unique for every victim, lest victims share keys with other victims of the same ransomware campaign, and that debilitates their entire campaign. So keys need to be unique, and in preparation phase, they will generate unique keys for this victim. Enumeration includes file enumeration, traversing directories, finding files of interest. Usually ransomware will not encrypt everything, but will look for specific types of files to encrypt. Encryption, finally, as that's the main idea, is to encrypt these files now in order to extract the ransom. Protection is to protect secrets until the ransom is paid, because that gives the leverage. So in our particular case, we're talking about keys. If they've encrypted the data using unique keys, then they need to protect these keys until ransom has been paid. This includes making sure there are no alternative routes to the keys that the victim can get to. Finally, there's extraction and ransomware extraction, ransom extraction, because ultimately financially motivated cyber criminals care about getting paid at the end of the day. So maintaining a viable extraction route is very important to them. And the last constraint is restoration. They should be able to restore data. Otherwise, there's a chance that if victims of the same ransomware campaign paid the ransom, but then obtained their files back, other victims are not motivated to pay anymore. So the last two are more operational constraints on the ransomware, whereas and they don't necessarily relate to the cryptographic functionality of the malware. So with that, let's focus on this hybrid crypto system. What you see on the left is an algorithm that discusses this hybrid crypto system. And in blue are highlighted the API calls on a Windows host. So these API calls represent abstracted functionality that the ransomware usually seek on the host. So it begins with something simple like crypto acquire context, which is actually establishing a relationship with the crypto API on the host. So on every Windows machine, there's a crypto API, and in later variants, there's CNG that has replaced the crypto API. But the idea is the same. You establish a crypto context, then you import the attacker's embedded public key. So remember, this is a hybrid crypto system. There's an asymmetric key, and then there's a symmetric key. Symmetric keys are generated on the system and used to encrypt data, whereas asymmetric keys come embedded in the ransomware binary. So we're talking about ransomware developers' public key, for example. And so this key will be imported into context, then a new symmetric key will be generated. Finally, there's a directory traversal loop, which looks for specific file types and encrypts those files using the generated symmetric key. And then this key is destroyed on the host, and any memory associated with any secrets is deallocated. This is to protect, this is that protection part we were talking about in the earlier slide. They want to make sure that they have unique access to the key once the encryption is complete. Finally, the ransom node is shown to the victim. So that's the basic functionality of a hybrid ransomware. Most ransomware today use this hybrid functionality, and that's why we're focusing on this. Well, so our solution is built upon some key concepts of memory forensics. One of them is that when the encryption is happening, the key will be exposed in memory. So that means if you look at the diagram on the left, it represents a symmetric key schedule held in memory while the encryption is ongoing. So there's a secret key, there's a master key that goes in, which is the key actually being used for encryption, let's say AES key. And a key schedule, so there's different rounds in the symmetric cipher. And for each round, there will be a round key, which will be pre-computed from this initial master key or secret key. And as blocks of plain text come in, they pass through the rounds. They are transformed within each round. So this entire key schedule is held in memory while the key is being utilized for encryption. So in and of itself, the asymmetric key will not have a structure, a defined structure in memory, but the key schedule in itself will have a structure. So we want to look for signs of that in memory in order to find the key that the ransomware is using. On the right, you see an asymmetric key in memory. Now, unlike symmetric keys, asymmetric keys do have a structure in memory. Sometimes it's a header. For example, in this case, we've depicted an RSA key blob in the Windows context. So in the Windows Crypto API context, this is the blob that you're going to see in memory. As you can see, there's a header which identifies that the RSA2 part over there in ASCII shows that it's an RSA private key in memory. Those bytes, the hexadecimal bytes, are all predefined when a particular type of RSA key blob is being observed in memory. So we can look for signs of that. So that's roughly the idea of discovering keys in memory. Now, how do we put this together with our solution? So in this diagram, you see the overall architecture of our proposed solution. We start on the left, where the key is exposed in memory during execution. So at this point in time, we're assuming that the ransomware is already in, and the ransomware has begun encrypting the files. Now the key is exposed while it's encrypting the files in physical memory. A component of our approach is using a trigger module. A trigger module can be replaced and is not an integral part of our solution. So for example, these are just indicators that a ransomware activity is going on the host. So as you can imagine, you can use any number of detection mechanisms in order to set off the trigger. In our case, we're using API calls. So for example, cryptgen random combined with find next file, those sort of API calls looks like something is going through the file structure and looking and generating random secrets and using those to encrypt files. So there could be other API calls in there which build API call graphs which show potential ransomware activity. Now we're not 100% certain, but it triggers off a suspicion. In this case, we will dump the key routine. We will trigger off the key routine, a key dump routine, which will actually scan the suspicious process for the presence of keys. So we will look in the process memory space. In our particular case, as a proof of concept, we used read process memory, which is a Win API call used to read the memory of a process. And the suspicious process's memory will be read. And so at the previous slide, I explained how we can look for signs of presence of keys. We will use those in order to discover potential keys in this memory space. And then a key convoy is responsible for securely transmitting these keys and putting them in a database. So it's very important that because we're not 100% certain that this is a ransomware process, if you're extracting any keys, you want to be sure that only the owner can decrypt these keys if needed. So there's a pre-established key pair that the owner uses in order to secure this whole system in the beginning. So at the time of installation, owner has a private key to the database, and the public key pertaining to this will be used to encrypt every key that is being discovered and being transported for offsite storage in the event of a ransomware attack. So the idea is that when a ransomware attack is noticed, the user or the owner can use their private key to reach out to the offsite database for the keys that the ransomware was using to encrypt the files. And that way we can decrypt the files and remove the leverage that the ransomware operators have and restore files. So how do we achieve that? We went through it in a series of steps. So the simplest step, simplest POC is we take a real world ransomware, and we have, for example, a JPEG image in this case. And so I know you probably can't read the bytes, but those are all bytes pertaining. So in the beginning, those are magic bytes pertaining to the JPEG image. And so we see those bytes, and then we see a ransomware process being triggered. And then the ransomware process using the crypto API will generate the C-MRiC key. So these are the hex bytes pertaining to the key. And using known encryption algorithms such as AES, the JPEG image will have its bytes transformed or encrypted. Meanwhile, the trigger will notice signs of suspicious activity and look for the key in the ransomware process's memory space and duplicate that C-MRiC key. And this duplicated C-MRiC key it was later used to recover the JPEG image. As you can see, we've restored all the bytes. So this was the experiment in its simplest form against a real-world ransomware, where we were able to have the ransomware encrypt the file in a controlled environment. By that, I mean a contained environment, and observe the files getting encrypted and then decrypt the files using the extracted key. On the right, you see key exposure durations. So as you can imagine, key exposure, memory is highly ephemeral. Things are changing constantly. So key won't be exposed forever. So that means that we have a limited time window before which the key would disappear. If everything was done correctly by the ransomware developers, and they make a lot of mistakes, but if everything was done correctly, best case scenario, we still have in that case, we will have a limited time to extract the key. In this right diagram, in this right graph, what you see is different languages. So as you can imagine, this key exposure time will depend on different things. How much data is being encrypted? What's the file size? So if there are large files, a large amount of data being encrypted, then the key will linger in memory longer because it's needed. Then if the CPU, how fast is your computer? If your CPU can process this encryption quicker than another CPU, then the key doesn't need to linger that long. So that affects it as well. And in this case, we were comparing against choice of language. So if as you can imagine, C++, a compiled language like C++ will leave the key exposed for less duration because the encryption happens faster. On the other hand, on the other extreme, like something like Python is going to take longer for performing the same encryption. So depending on the language, depending on the host system's capabilities, and certain other factors, how much data is being encrypted by this key, the key will linger in memory for a finite duration. So this is our algorithm in short that we used to discover the key. So once a suspicious process has been identified, we process the memory bytes. By that, we mean we look in the process's memory space using a call such as reprocess memory. As we start processing the bytes, we need to look for signs of a key schedule. So we will take the current number of bytes that equal the key size we're interested in, and then we will match the bytes that immediately follow these bytes. We will compute a key schedule out of these current bytes, and then see if the bytes that immediately follow match the computed key schedule. If they do, then we have found a key schedule in memory, and that means we've found a key. So if not, then we move the offset and move forward and look for, again, repeat the process. So that's the general idea behind discovering keys in memory. We've used this approach against several real-world ransomware. We demonstrated the tests. So this is a smaller subset of ransomware. Our paper contains a bigger subset, but it's still finite because at the end of the day, we're repeating the same experiment, but with different ransomware. If they all have the same hybrid crypto system and they're generating the key similarly, then proving it for a few means we're proving it for a larger subset. so we were able to extract the key and perform data restoration. So the primary insight, in summary, of our work is that cryptographic keys are exposed by ransomware during the process of encryption. And this is true for all ransomware, and it doesn't matter what API they're using, since those key schedule will, the signs of the key schedule that we're looking for will be present in memory, no matter what API is used, no matter what language is used. And so that's, unless a ransomware is using white box cryptography, they're probably exposing, they're definitely exposing keys in memory. So, so that's the primary insight. And the main technical challenge we faced was the volatility of physical memory. As you can imagine, physical memory is constantly changing. And so you can't make assumptions without doing a lot of experiments to see what's actually really there. The data is highly ephemeral, so we're bound by time as well. If, you know, if we take too long, the key might have appeared and disappeared in memory before we could get to it. Existing solutions focus on the prevention and detection part of the NIST cybersecurity framework that I introduced earlier. We want to focus more on the response and recovery side. So, and the methodology that we used is recognizing the key structures in memory to extract the key, as we've been discussing. Result that we've obtained is we've decrypted files encrypted by several real-world ransomware. And in our future work, we want to test it against a larger set of multi-key ransomware strains, because they introduce another layer of complexity specifically to the solution, because they use different keys for different files. Now that means that a key will not, if they do everything properly, the key will not need to be exposed in memory for a long duration. So we need to test more around that and discover the constraints on our solution in that respect. We also want to experiment with different trigger conditions. In this one, I mentioned the API call graphs. There could be better trigger conditions. That part of our solution architecture is highly modular, so it can be replaced by another triggering solution. Ultimately, the point is to detect the presence of suspicious ransomware-like behavior. Finally, there's another problem introduced by multi-key ransomware that are using different keys for different files. If we extract a set of those keys, in that case, we need to figure out which key goes where. So we need to somehow figure out a methodology to provide mappings for which key was used to encrypt what file. In conclusion, we're focusing, as I mentioned several times during this presentation, we're focusing more on the response and recovery part. Backups are not always sufficient, as has been proven multiple times. The defense in depth is the real true solution against a problem as severe as ransomware. And to that end, we're defining another layer in the defense, in the layer defense. So this is not meant to substitute any identification, protection, or detection parts that you already have. It's only meant to augment what you already have and just be another layer in the defense. Finally, it's important to have scalable solutions. If a solution is coupled too tightly with an operating system or with a particular API, or a particular ransomware language, in that case, it becomes limited in its applicability. So to that end, we would like to make it clear that this approach does not depend on the use of, for example, Windows Crypto API. If they use another API, ultimately the key schedule will still be held in memory. So, so that's an advantage we have. And with that, we conclude our talk for today. Please let me know if you have any questions. Thank you.
Thank you very much, Pranshu. It's been very interesting. We have few questions for you. So Sean is wondering what could happen if ransomware authors, they start bringing their own crypto APIs, potentially just making some trivial modifications with existing ones.
Right. So I believe Sean is talking about the trigger part of our approach. as I've said in the presentation, that part is modular. If we notice a scenario where ransomware do not make those API calls and avoid detection, we can always substitute another detection approach that works better. For example, machine learning could be used. For example, there's always other approaches that can be substituted in our solution. And yeah.
There's another question from Tolga, who is asking, how is the monitoring of the crypto APIs executed by an application?
Right. So there's different ways of monitoring crypto API. There is, for example, DLL based monitoring. So in that case, every call that is going to those particular DLLs that crypto API or the CSP is comprised of will be monitored in the memory. And those DLL hijacking, so those sort of import address table hijacking and DLL hijacking have been documented. That is not a novel part of our solution, but if somebody wants to know more about that, I recommend reading up on import address table hooking.
Great. So we have another question from Tapadir, who is asking, how efficiently have you been able to detect the keys from the process memory?
Right. So in terms of efficiency, we have been able, so with this preliminary experiments that we've done, if the ransomware is exposing using the single key, which a lot of them do, if they're using the single key for encrypting your entire file structure, in that case, we have a great amount of success. Because the key is exposed for longer durations and we have a longer time window. Now, in terms of multi-key ransomware, we need to make our solution more efficient, simply because if the ransomware is properly written, is well written in a language like C++, for example, we will see keys appear and disappear in memory very quickly. And we're talking milliseconds if the file size is small, and seconds if it's a larger file size. In that case, we have been able to extract a set of keys. However, we need to do more experiments around that, around the multi-key to determine the true efficiency there.
Okay, thank you very much. With that, we have covered most of the questions. So it's been great to have you around.